Good afternoon and welcome to today's Electronic Design webcast. Our topic today is From ADAS to AVs, Powering Next Generation Automotive Solutions, sponsored by Avnet. I'm Bob Vavro with Endeavor's Design Engineering Group. Let's talk about how you can participate in today's presentation. If you have any technical difficulties during our session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. If you need technical assistance solving common issues, please click on the yellow help icon below the slides. We also welcome your questions during today's event, and we'll get to as many of those as we can during the Q&A session that will follow the main presentation, so feel free to send in your questions at any time. To do so, simply type your question into the question window on the side of your screen and hit the Submit button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website beginning within the next week. You'll be notified by email when the archive is available. So let's meet this afternoon's speaker. Murray Slovic is the Editorial Director and Principal of Intelligent Tech Content, an editorial services company that provides technical articles, white papers, and social media posts for clients in the electronic design, semiconductor, and consumer electronics industry. He's trained as an engineer and has more than 20 years of experience as a chief editor of publications covering electro technology. You can learn more about Murray by clicking on the blue speaker bio widget on your console toolbar. So Murray, good afternoon. Welcome to our presentation. Looking forward to today's webcast.
Thank you, Bob, for that nice introduction. And welcome to From ADAS to Autonomous Vehicles, Powering Next Generation Automotive Solutions. Today, we're going to discuss what's in store for the automotive industry as the next generation of ADAS technology emerges. We'll examine some challenges facing OEMs and Tier 1 suppliers as they brace for new curves in the market. ADAS and autonomous driving both depend on extracting useful information from various sensors in vehicle cameras, radars, LiDAR, that all sense information on the outside world. ADAS development leads directly to the development of autonomous vehicles. Currently, ADAS is generally positioned at level 2 of autonomous driving, if you're familiar with the Society of Automotive Engineers listings. This means that the driver is still the decision maker. So while level 5, which is fully autonomous vehicles, where the vehicle can perform all driving functions under all conditions, are still some distance away, ADAS is progressively shortening that distance. Before we start, a word about the 800-pound gorilla in the room. And I'm talking, of course, about the pandemic. Market researchers are in the process of pivoting their research projects and plans in light of the COVID-19 pandemic. It's taking its toll on the global economy and has forced plants to shut down, it has disrupted supply chains, and it has quarantined workforces. Market researchers are now trying to incorporate the pandemic into their forecasts and projections. But it will be a while before accurate forecasting can take place. So please don't expect to see specific ADAS market size predictions in today's presentations, because what might have been true a couple of months ago likely is not true now. But there is encouraging news. In March, the Automotive Supply Chain and Technology team at IHS Markit conducted a survey among executives of automotive suppliers across key regions to capture the perception of suppliers regarding the impact of the COVID-19 pandemic and what it has had on their manufacturing operations at the supply side. Now, let's take a good look at this slide. You'll see that in red, the question that was posed is, how long will it take impacted plants to return to full-scale production? You see the red, 29% said within 1 month. The aquamarine, 16%, 1 to 2 months, which means that 45% of respondents said that they should be back and running fully within 2 months of the startup. If you add in the Violet, who said 2 to 3 months, now you're talking about fully 61% of respondents said that in a span of 3 months from startup, they should be back in totally full operation. And that's actually pretty good news considering. Now, we've had reopenings across the world, in the U.S., in fact, yesterday. And the reopening of the U.S. auto sector manufacturing side will be closely watched as a test of whether workers across a range can return in large numbers without a resurgence of infections. How well the automakers do will be significant for the U.S. economy, as nearly 1 million workers are employed in the sector. In Europe, Ford has gradually restarted production, beginning with its facilities in Germany and Romania. Volvo has resumed vehicle production at its Torslanda, Sweden facility. Volkswagen AG has restarted car plants across Europe. The Daimler's Mercedes division has restarted production of powertrains and plants in Berlin and Hamburg, and others such as the Peugeot Group and Renault are slowly bringing plants back online. And by the way, if you've been spending the last couple of months anxiously awaiting delivery of your new Bentley, I can tell you that the British luxury brand restarted production on May 11th. Okay, with that in mind, let's take a look at today's agenda. We're going to start by looking at how ADAS will be the enabler of both driver-controlled and autonomous vehicles going forward. We'll then describe what these capabilities are. We'll look at sensor technologies making ADAS possible. And then we'll examine artificial intelligence and near-future ADAS functions. And finally, we'll have a brief wrap-up followed by a Q&A. Okay, now let's look at the technologies needed to eventually get to autonomous driving. Okay, when most people think about automotive technology, many don't realize the depth and breadth and complexity of where we are really heading. People understand the idea of the connected car, but not the immense infrastructure being developed, which in its entirety is known as V2X. V2X is changing the game. It is accelerating development of systems and of module-level solutions. Autonomous operation will require video-to-everything communication between the car, other cars, and the surrounding infrastructure. There are, however, issues. In 2017, the administration announced that it was killing a previous mandate that would have required new cars to be equipped with vehicle-to-vehicle technology and set aside 75 megahertz of spectrum in the 5.9 gigahertz band for what was then being called dedicated short-range communication services. Then last year, tensions escalated when the FCC put out a new plan to use some of the spectrum set aside for V2X to instead expand Wi-Fi. This issue is yet to be resolved, and it will have to be resolved if self-driving cars are to become a reality. Let's now take a look at ADAS as a key enabler. Most cars today come with some sort of ADAS functionality. According to the AAA, at least one ADAS feature was available in 92.7% of new vehicle models in the United States in 2018. Drivers are increasingly counting on these systems to improve their driving, to reduce distraction, help them focus on the road, and enhance road safety. ADAS and automotive driving both depend on extracting this useful information from various sensors. That said, full automation already exists in a few Level 2 systems. An example is the one that's in a Mercedes-Benz GLO class vehicle, which already can execute changes automatically. But, and it's a pretty big but, Developing vehicles that are verifiably safe by design is critical to enabling higher levels of autonomy on the world's road. Most road accidents occur because of human error. ADAS systems automate and adapt and enhance vehicle systems for safety and for better driving. These features are designed to avoid collisions and accidents by offering technologies that either alert the driver to potential problems and in some cases take control of the vehicle. But these systems must be fail-safe for ADAS to maintain traction on the regulatory and consumer fronts, and they're essential if consumers are going to be confident enough in the car's ability to drive itself. Okay. Let's take a look at a case in point on industry cooperation. And the takeaway that I want out of this is between the United States and Europe, there are two different ways of approaching regulation. In Europe, regulations are still being written that kind of mandate industry cooperation on the specific technology involved. The United States, and particularly the current administration, has stepped away from mandating things to private industry. So instead, what tends to happen in the United States lately is that there are recommendations and there are voluntary programs that are generally administered by the National Highway Traffic and Safety Administration, or NHTSA. But the point of this slide is that you can have, if the technology is good enough, and if the industry believes in the technology, simply posting it as a voluntary thing doesn't necessarily mean people will go along. As you can see on this slide, 20 automakers have voluntarily agreed to accept on new passenger vehicles with low-speed automatic emergency braking and forward collision warning by September 1st, 2022. And if you look at the last few in green on your right, you will see that Tesla, Volvo, Audi, and Mercedes have already met their voluntary commitment under the agreement. And that's 3 years ahead of schedule, 2.5 now. And as of August 31st, 2019, 12 manufacturers had equipped more than 3/4 of their new passenger vehicles with AEB. 2 years ago, you would have found only 30% of these new vehicles would have been equipped with the function. So, is AEB effective? In a word, yes. In the United States, the Highway Loss Data Institute compared rates of insurance claims per insured vehicle for Volvo's S60 and XC60 vehicles, which were equipped with standard low-speed AEB with comparable they compared them to vehicles without the function. Volvos with the low-speed automatic emergency braking had 18% fewer collision claims, which covered damage to the at-fault driver's vehicle. In the UK, they did a similar study, and the XC60 SUV models with standard low-speed AEB experienced 6% fewer owner at-fault claims, which is essentially saying that the system works. Are consumers ready? Again, from an acceptance perspective, ADAS helps consumers because it gets them accustomed to allowing machines to do the work for them, which is necessary if you're going to get acceptance of self-driving vehicles. Many ADAS features help drivers better monitor vehicles and the environment around them, and it teaches humans to trust cars more and ultimately to rely on vehicle technology to help them make good driving decisions. Increased trust in these types of capabilities will give consumers a more comfortable feeling with an autonomous vehicle. So how we get to trust in self-driving technology? Through existing ADAS capabilities. Okay, now let's take a closer look at the functions that will soon be found across most major auto models from entry level to luxury class. The list of ADAS features on the road has grown significantly in recent years. You'll see how many of these. If you look at the slide, you see cameras, you see radar in operation. Let me take a second to explain what intelligent headlamp control is, because you might not be aware of that. That's controlling the beam of light at night that comes from the car so it doesn't blind the driver coming at the car in the other direction. Now, that's different from high and low beam, because high and low beam essentially just changes the intensity of the beam, but not the direction the beam is going. But with LED and soon-to-come laser lighting, you can control where that beam is going to land, and you can then find through the other sensors where the oncoming car is and ensure that you're lighting up the road in front of you, but you're not blinding the driver who's coming at your car. Okay, let's go to one specific, automatic emergency braking, which I mentioned briefly a moment ago. Many drivers can now rely on this feature. On-vehicle sensors, including radar, cameras, and lasers, detect an impending forward crash with another vehicle in time to avoid or reduce the severity of a crash. The first interaction with the AEB system is an alert that the driver will get to take corrective action. Then the system will supplement the driver's braking to avoid the crash. If a driver brakes but not hard enough to avoid the crash, dynamic brake support kicks in, and that supplements the driver's braking in an effort to avoid the crash. If the driver takes no action to avoid the crash, then a related system called crash imminent braking automatically applies the vehicle's brakes to slow or stop the car, avoiding the crash or reducing the severity. We've all either experienced AEB in some form, because it is in a number of cars now, but we've also experienced some functionality that some cars, and maybe you have experience with this, is you get in the car and you buckle your seatbelt and you start driving, and all of a sudden, when you're over 5 miles an hour, that you feel a little tug on the safety belt, which is self-tightening for your prevention. So all of this is getting people ready for driver assistance functions on the road to autonomous driving. Crash imminent braking and dynamic brake support that meet the required performance specification are rated by NHTSA as recommended safety technology. I mentioned a couple of moments ago that in the U.S. here we're kind of out of the business of mandating these kind of things, but NHTSA does list for consumers the recommended safety technologies that they ought to be looking for when they're in the market for a new car. We've come quite a long ways. If those of you who, like me, are old enough to remember when, say, Ricardo Montalban in his Chrysler Red was pushing the rich Corinthian leather. Well, that's still a factor in buying a car, but the smart consumer would actually also go to NHTSA to see what of these functions that the organization is recommending. Let's take another example that you may be somewhat familiar with, because most cars have cruise control. And adaptive cruise control is an intelligent system that allows the driver to maintain an optimum distance by allowing the vehicle to automatically adjust its speed. In most current cruise controls, there's a little button or switch which is positive and negative, and you can increase the speed or decrease the speed while still remaining in cruise control. Essentially, adaptive cruise control does that for you. It judges where the car ahead is. It determines what the speed of the two vehicles are, and it does what it needs to do in terms of accelerating or braking to maintain a given distance. So it's more distance dependent than it is speed dependent. It's installed in the front of the vehicle. As I said, it monitors the road ahead, and as long as everything is clear, it maintains the speed set by the driver. But if it sees a slower vehicle, it gently reduces speed by releasing the accelerator or actively engaging the brakes. The point to remember is that even with adaptive cruise control switched on, it is still the driver's responsibility to monitor the speed and the distance from the vehicle in front of him or her. Forward collision warning. Again, a distance is being measured of the car that's in front of you. And it will notify the driver in case the system senses that a forward collision with any other vehicle or object in a roadway is imminent. When the distance becomes so short that a crash is imminent, a signal alerts the driver so that the driver can apply the brakes to take evasive action, such as steering, to prevent a potential crash. Some forward collision warning systems are integrated with the adaptive cruise control system that I just mentioned to slow down the vehicle when another vehicle is detected. Blind spot warning. It uses camera or radar to monitor vehicles approaching from the side that the drivers can't see, the area that's next to or behind the car, in what's called the driver's blind spot. Again, the idea is to facilitate safe lane changes. If a vehicle is detected, the driver gets a visual warning, often in the mirror, or it's the outboard mirror, or on the front pillar. When a system detects a driver driving in an adjacent lane approaching the rear of the driver's vehicle, which is the blind spot area, it notifies the driver. There's either usually an audible warning or in some cases a tactile warning. The steering wheel might start to shake, for example, as an alert to indicate that it's unsafe to merge or change lanes. There's another type of blind spot warning, which is blind spot warning with automatic emergency steering. In this case, the system steers or brakes when the turn signal is activated during a lane change maneuver, when the system senses that there's already another vehicle occupying the blind spot in an adjacent lane. Okay, lane keeping support. I just was talking a little bit about changing lanes. And this particular system, the lane departure warning, uses a camera, monitors lane markings, and detects when a vehicle is drifting out of its lane of traffic. Again, when the vehicle is detected veering out of its lane without the turn signal turned on. And in almost all cases, turning the turn signal on alerts the system to not go active. But if you haven't turned the turn system on and you're trying to go into or you're veering out of a lane accidentally, you'll get again an audio, a visual, or another alert warning you of the unintentional lane shift, so that you can steer the vehicle back into the lane it is supposed to be in. But again, it's not fail-safe because it is a vision system in most cases, and it's not perfect. It doesn't work well in rain or snow because it's camera-based, and it will shut down, sending an alert to the driver when visibility is limited or there are no lane markings at all. This can occur on a highway where you're reaching an exit and the markings stop at the exit, and the system has to relate on less visible markings that remain, and also has to scan the road for where the marking picks up again. Another area of weakness here is when the lane markings are old when instead of the common painted stripes that you have, there are some cases where you may have dots, and those are more difficult for the system to pick up. More vigorous programs to fix road surface markings before they fade would be helpful in supporting machine vision and will be essential for proper operation of self-driving cars. Some systems have lane keeping assist, which uses automatic corrective steering input, which is to say, it will try to steer, rather than simply give the driver a warning, it will try to steer the car back into the lane from which it was driving. Again, if the turn signal is not put on when a lane shift is occurring. Some of these systems work well, some of them don't. I have this on my car, and it can be a little bit annoying in a sense that, let's say you're driving along in a lane and you see this huge lake-like pothole that's in front of you. So, not wanting to risk damaging your tires, your suspension, or both, you swerve briefly, you check to see if there's any traffic around you, and you swerve briefly around the pothole into the next lane. Well, if you haven't signaled, and usually these things come up so quickly in your view sight that you don't really have time to signal. You just make the evasive maneuver, and then the car tries to put you back in the lane from which you came from, and you end up fighting the car to gain control. Now, you can win because by vigorously turning the wheel the way you want to go, the car will eventually go where you want it to, but it is a little bit annoying, and most of the systems that I've had a chance to try, that you do in circumstances like this have to fight the car a little bit. Now, I will talk later in today's presentation about artificial intelligence, and AI certainly will play a role in identifying a possible reason why you might be swerving out of a lane and keeping this function well in hand. Okay, backup camera. A rear view system known as a backup camera is a safety technology. It prevents backover crashes, protects our most vulnerable people, children, senior citizens. By providing an image of the area behind the vehicle, when a driver shifts into reverse, the camera shows either in a dashboard display or a small display on the rear view mirror an image of the area behind the vehicle. The field of view generally includes a 10-foot by 20-foot zone directly behind the vehicle. I mentioned a couple of times now that NHTSA is somewhat out of the business of mandating safety equipment, but in May of 2018, NHTSA did require the backup camera technology on all new vehicles. Let's talk about another safety measure that some of you may be familiar with, and that's parking assist or advanced parking assist. Again, the lane markings are determined, the target parking position of the vehicle for parallel parking is determined. Sensors monitor the size of the potential parking space as you drive by, and in some cases they will alert you when a good fit has been located. And usually the alert is an arrow on the dashboard telling you, look to your right or left, there is a potential parking space. Once the space has been found, all the driver has to do is, as you see in the slide, is pull up next to it, bring the vehicle to a stop, and shift into reverse gear. Shifting into reverse gear causes a grid to appear, usually with colored green or red lines, representing the corners of the parking spot, and adjustment arrows on the display, eliminating guesswork and assuring a perfect parallel parking job with no risk of damage to the vehicle or the system or other vehicles. Okay. In our next section, we've been talking about ADAS technologies, and I've been mentioning all along the sensors that are required for these technologies to function. So now let's take a little bit closer look at exactly the sensors that are involved. Okay, as you'll see from this slide, there is an array of sensor devices that are used for ADAS and will be essential for self-driving cars. Radar, both long range and short range, LiDAR, which I will talk about shortly, which is laser-based, cameras, and ultrasonic sensors. The idea here is for the sensor to provide a fail-safe 360-degree view around the vehicle for the applications such as collision avoidance, adaptive cruise control, blind spot detection, lane departure, all of which I just mentioned, and even some that I haven't indicated, such as traffic sign recognition. With artificial intelligence and machine vision, it will be possible for the car to not only see a given road sign, but also to understand what the road sign stands for, and if there are words on it, what the words represent. This is going to take, in some cases, a little bit more unification globally of the signs and the languages involved. But again, if we're going to get to self-driving car, the car, like the driver, has to know what the sign says. Okay, let's take a look at camera systems. Camera systems are the only one right now that can reliably identify not only that there's an object, but what the object is. When combined with optical character recognition, the car can tell what the posted speed limit is. It can tell if there's a temporary construction speed limit or an accident or fog alert from an overhead sign. Again, this involves machine vision and in some cases artificial intelligence. If you have a color camera on the car, say on the windshield, the car can even tell when the traffic light goes green. It is not meant, however, for drag racing. Camera systems have issues. In rain, snow, fog, darkness, or a bright sun, their ability to detect what's going on does diminish. And because of these limitations, the data from image sensors is being combined with other sensors such as radar to provide a more robust and a reliable data stream across a wider variety of conditions. A little bit later in today's presentation, I'm going to be spending a bit of time talking about sensor fusion. What sensor fusion is essentially is taking the input from radar and LiDAR and ultrasonics and cameras and combining them and using one to check against the other, so that if you're getting a report from one sensor that there may be an object out there, you want to confirm that fact with a backup sensor of a different kind. But I'll talk a little bit more about that momentarily. Radar. Radar basically works by measuring the time it takes for transmitted radio waves to reflect back off an element in their path. It is well suited to seeing other cars, not just at a distance, but it can determine how fast the obstacle is moving thanks to the Doppler effect. And for those of you who don't remember Physics 101, the Doppler effect is a change in frequency or wavelength in relation to an observer moving relative to the wave source. For ADAS functions, radar has moved from 24 gigahertz to a more efficient 77 gigahertz, which offers higher resolution and greater accuracy for speed and distance measurements. There is at the bottom a solution highlight that you see from our partner Xilinx, which has got a system for vision, which can do the necessary hardware acceleration and image adjustments from the camera system, and also works nicely with radar. Okay, LiDAR. Light detection and ranging. Works on essentially the same principle as radar, but uses lasers to generate high-resolution 3D map of the world around the vehicle. And what you see here in the slide is an actual image developed by a LiDAR detector. You see it's good at projecting 3D images. It enables a self-driving car to have a 360-degree visibility and accurate depth information to an accuracy of plus or minus 2 centimeters. It can detect an exact size of an object and identify details in an object from a few centimeters distance to more than 100 meters distance. It works well in all light conditions and is unaffected at night. Performance does drop a little bit in snow, fog, and rain, but it doesn't drop as much as a camera system will in the same conditions. LiDAR cannot read letters on a road sign that cameras can. It can because the markings are in 2 dimensions, so it's not good for things like lane departure warnings. It also requires a very big amount of processing power because it's getting up to 1 million measurements every second, and that these have to be translated into actionable data. So if you're using LiDAR, you're going to have big-time computing power to go along with it. The reason that LiDAR is appearing on prototypes and working models of self-driving cars is they need the computing power anyway. So it's going to be there for that kind of vehicle, but is not currently available in a commercial vehicle that you drive yourself. Because of all of these factors, cost is a factor. The original self-driving car prototypes had a LiDAR system that was in the neighborhood of $75,000 to $100,000 just for the lasers, the laser system, entire system. Obviously, that's not going to work if you're talking about mass production. But like most common technologies, it's expensive at first, and it becomes more affordable later. That was true, for example, in the Consumer Electronics Show 2020, which did take place before the pandemic spread around the country. There were several models, initial development models, of LiDAR systems for lower-end applications, but the point is that they cost only around $100, and Velodyne and others are working on bringing the cost down so that the technology will be available for both very advanced ADAS and, of course, for self-driving vehicles. Ultrasonics, reflected sound waves, not unlike what a bat does, to calculate the distance to object. The latest generation, I mentioned automatic and remote parking. In most cases, because of the short range involved, the parking system relies on ultrasonics. It supports emergency braking, at low speeds by detecting objects that are close. It has relatively fast reaction to suddenly appearing obstacles. And a lot of these things, when you're talking about an imminent crash, you're talking about having a car that has to change what it's doing very quickly. Latency is a major factor. How long it takes for the sensor to pick up a potential object transmit that information, and have the car system react to that object. This has to be done very quickly, especially if you're at highway speeds. Where latency becomes something of an issue in self-driving cars is you also have the issue of security. And you want to make sure that the information coming from all of your sensors has been protected so that it can't be hacked. Well, in a lot of cases, what you do is you put in an additional security layer so that you're fairly confident that you're looking at a real signal. Problem is that in the real world, adding a security layer is going to take a small but measurable amount of time. And then the question the engineers are struggling with is what's acceptable? Where's the trade-off here? Because you want to have the system react as quickly as possible, and yet you also want to make sure that the signals you're reacting to are genuine. So it's a significant engineering problem that people are working on. As I mentioned a couple of minutes ago, sensor fusion. Cars today are being fitted with a number of environmental sensors that perform a multitude of tasks, but one type of sensor cannot safely monitor the conditions around the car in all situations. For example, cameras may not be able to recognize other objects in low visibility, as I've mentioned. Radar has its limitations. LiDAR has its limitations. But by synthesizing the input from each sensor, technology solutions can be found so that data from the individual sensors working independently would be unable to generate by themselves. You're creating a 1 + 1 = 3 system, in effect. It's a multiplier effect. You want to have a redundant monitoring system with different types of sensors used for the same application to ensure that the right information is always getting to the vehicle, whatever the road condition. This is known as sensor fusion, and it's the best way to determine if the car appearing on radar is the same as the object being seen on LiDAR or by a camera, increasing the reliability, range, and accuracy of overall results. Again, on the bottom, Xilinx has a solution. It's a software platform that tailors architectures to the software or the algorithmic code so that the engineer doesn't necessarily have to be a hardware expert in this case. The Glass Cockpit. Again, and if you drive a modern or a late model car, rather than the analog gauges in front of you, what you're seeing basically is a digital display. And you might also see that at least one of the two, not the one behind the steering wheel, obviously, but the display that's generally to the right of the driver, either above or in the dashboard, the one that's being used to control air conditioning and to control the entertainment system. More often than not now, that's a touch screen. And one can argue about, the safety margins involved because you're going to have to take your eyes off the road for a very brief period of time in order to sort of look over there, stick your finger there, and hit the necessary area. And for that reason, as the costs come down, I think you're going to see more, heads-up displays where the vital information, up to and including navigation information, is displayed on the windshield in front of the driver, so the driver can see it at a glance without having to take his eye off the road. But we're going to see more glass cockpit solutions. Now, they're also going to require a bit of computing backup because to work really well, they have to have, the throughput has to be a minimum of something like 30 frames per second, so you get real resolution and you can identify exactly what it is that you're looking at in the display. These displays almost universally are LCD, like most of your home televisions. And two requirements that you need to know about this for strategy and planning purposes. It's not a proprietary play. Digital display hardware must be usable among multiple car models with different feature offerings. And it also has to be scalable and adaptable. It has to be adapted as connectivity is added or updated as networking standards change over time. And it's not just networking standards. These systems, like Apple CarPlay, for example, link up to your phone, and we know how rapidly phones change systems and change how they do things. And the car system, and especially the Glass Cockpit and the entertainment display, is going to have to keep up with changes in personal phone use. Okay, artificial intelligence and machine learning, plus, as I say down there, what's next? AI, in a few words, is changing how vehicles are designed and built. Okay, just let me. Great. Okay. Here's how AI is changing the industry in several ways. Automobile production. It'll help to eliminate equipment failure and in this way bring down the cost of manufacturing and of selling automobiles. If a machine fails unexpectedly on an assembly line, you can imagine the cost can be catastrophic. Not just stopping the line, idling employees who are unable to complete their quotas, and a whole factory can be thrown into disarray. What AI algorithm does in this case is that it digests the masses of data from vibration sensors and other sources. It detects anomalies. It separates errors from background noise, diagnoses the problem, and predicts if a breakdown is likely or imminent. And you'll be hearing a lot on the manufacturing and the Industry 4.0 side on predictive maintenance. I'm saying, look, this is likely to happen in the next time period, and it gives the people on the maintenance side an opportunity to either fix it before it breaks or to be better prepared for a breakdown should one occur. In terms of other, I mentioned just now the increase in availability of factories that go over to AI. There was a study by the McKinsey Global Institute who predicted that AI can have a 20% increase in equipment availability and reduce inspection costs by 25% and reduce overall maintenance costs by 10%. Okay. Now, why AI in the car itself? Well, for one thing, a lot of what I've been discussing requires computing power. And conventional computing is simply not up to the task, and it's certainly not up to the task of controlling a self-driving vehicle. Driving a vehicle involves more than following a given set of rules or an algorithm. It involves learning. In other words, it requires AI. Human driver can instinctively determine driving conditions and the effect it's going to have on what he or she does on the fly. But developing rules for every possible combination is impossible. You can't simulate to that extent. And to try to do it on the road would require driving literally millions of miles of test driving. An example, things that are difficult even to teach, to do machine learning with a self-driving car. Let's say you and your car drive up to a railroad crossing, and the gate is going to start to come down, and the lights are flashing, but the gate is still moving. Now you, being a safe driver, you come to a stop. Now, what's to say that the guy behind you isn't going to try to be an idiot and is going to try to beat the gate down and beat the train across? The car and the intelligence running the car has to understand that this is a moronic move. Don't let it affect you. But again, it's an example of the myriad of driving situations that occur that can't be absolutely predicted in advance, and that a car and the car system, especially for self-driving car, is going to have to react to at the moment. And that's what machine learning in the car is going to do. By the way, the picture here is Mercedes-Benz MBUX interior assistant. It was developed in conjunction with Xilinx. It uses artificial intelligence to recognize the natural movements of the occupants, as well as the context of those movements, so the vehicle can actually predict driver and passenger needs and accommodate them without the driver having to push any buttons. Okay. Intelligent speed alert. This depends upon, in most cases, GPS and your navigation system, which now are generally good enough to know what the speed should be. And in some cars, even current model cars, when you're driving along, it'll flash the speed limit on the general display in front of you. And in most cases, that's all that it does. It gives you a sort of an idea of what's to happen. But we're going to start to see these systems, particularly in Europe, and I mentioned 2022, when a bunch of safety systems are going to become mandatory, where having this provision on the car will become required. And in some cases, although it's yet to be determined, whether they'll take the next step, which is to prevent you from exceeding the speed limit. My guess is that won't happen, that this will simply be advisory, at least in the beginning. But, the day, the one thing that autonomous vehicle won't do is speed. So we might as well start to get used to that fact. And so you might see down the road in a few years some ADAS systems where the speed limit, a speed limiter, which you will be able to override, but at least initially might be put into play to keep the car at the required speed limit. I mentioned the European Commission in March of last year approving the rule to make intelligent speed assistant mandatory for all newly manufactured vehicles. Okay. Let me quickly go through a couple of more. Next up is pedestrian automatic emergency braking, which is like standard automatic braking when there's a car in front of you, but this will take place when there's a pedestrian involved. And again, NHTSA has recognized this as a promising technology that might be added to its 5-star safety rating. The point I want to make here, this is about generic steer-by-wire. This is the way steering systems are developing. You'll notice there isn't a direct mechanical link between the steering wheel and the actual front axle and rack and pinion steering. There's a computer in the middle. You turn the wheel, it's translated into digital information, and the computer takes it from there. Where did this come from? came from fly-by-wire, came from aviation, where the pilot is moving the joystick, but again, all he's really doing is sending information as a request to a computer. Again, when you have the computer in the system, you can do automatic emergency steering, and basically what this slide is showing is a car that is determining how to get around another car that it might be crashing into. It determines where it needs to go. It determines the exact trajectory around the car, the additional steering torque that will be needed to follow the trajectory and to stabilize the car. Again, if braking alone won't do it and it gets to a sort of an imminent bad situation, as we get further down the road toward self-driving vehicles, you'll have autonomous emergency steering. The last of these features that I'm going to talk about, again, you're going to see very soon, is rear occupant alert. Leaving a child, or anyone for that matter, in a parked car in hot weather is an invitation for disaster. So we're already seeing systems put in place that will alert you via your phone if you've left the car that there's something going on in the back seat. It depends on an ultrasonic system. Hyundai has one already. When the engine shut off, if the back door has been opened prior to driving somewhere, which tells the car that there may be somebody in the back seat, it provides an audio and a visual alert. Motion Center will sound the horn, it'll flash the lights, and send a notification to the owner's smartphone if an occupant is detected inside the back seat for up to 24 hours. Okay, now for the big finish. Here are some takeaways that we would like you to get from today's presentation. ADAS functionality is continuing to be innovative. V2X communication is going to be a necessary part of that. Autonomous vehicles are still some years away. ADAS is shortening the distance. These functions are available, and as I've mentioned, things like automatic emergency braking have enable fewer collision claims. Consumer acceptance will pave the way to success in self-driving cars. Sensor fusion is essential, and artificial intelligence is changing the industry and forever. We now have a few minutes for some Q&A, so let me turn it back to Bob. And thank you for your...
Thanks very much, Murray. We will get to a couple of questions here as time permits. If you still have any questions you'd like to submit, type them into the question window on the side of your screen and hit the submit button. And while we're answering those questions, please also complete the feedback form, which is located on the bottom of your screen. We do have a couple of time for a couple of questions here. One question is, I understand the auto industry and the FCC are at odds over V2X communication. So can you tell us what's going on?
Yeah, I mentioned it a little bit in the presentation. I'll give a little bit more of information on that. A trade group called the Alliance for Automotive Innovation represents most of the major automakers and suppliers. About a month ago, released a statement saying that they will install 5 million pieces of V2X equipment over the next 5 years, provided that the FCC reverses its decision to repurpose the airwaves that have been set aside for V2X communications. In other words, yeah, they're willing to use the frequency for V2X, but the frequency has to be there. And if the FCC is serious about giving that away to cell phones, then the only choice that the industry has will be to go to a cell phone-based system. And that works and it has been tested, but it's not preferable to everybody in the industry. And I think the industry would rather have a choice and would rather have the airwaves available for V2X that they were initially promised a few years ago.
Very good. One other last question here. Can you give us an example of how AI is being used in the car itself?
Yeah, I mentioned traditional, I mentioned computer vision. And AI is actually for things like forward camera perception. What the camera is seeing is what AI is determining, in much the same way as it's used in security for image recognition. So that if a face appears on a camera, then the security forces can apply AI-based systems to help determine who that person is. Now, that's not going to happen in a car, but determining that it's a person, determining that it's a dog crossing the road, determining that there's a road sign that says something, that's an example of what AI is going to be able to do. Another quick example is within the car, measuring the driver and the driver's performance. Once the system gets a read on what the driver normally does, if the driver is incapacitated or, God forbid, has a heart attack or something, the system looks at him or her and can immediately determine that there's something wrong, what the something is, and summon help.
Very good. Well, that's a good place to stop. This is a great presentation by Murray, and I appreciate his time and also the questions that we've gotten. If we didn't get a chance to answer your question, we will be in contact after this webcast to get all those questions answered for you. So that concludes this afternoon's presentation. On behalf of Electronic Design, I want to thank Murray again for his presentation and Avnet for sponsoring today's event. And of course, thanks to all of you for joining us. Have a great rest of your day and stay safe out there.